Have you ever been buried under, just mountains of notes or old files, trying desperately to find that one specific thing you need?
Oh, definitely. Or maybe you've gotten like 3 different emails from the same company about the same promotion.
Exactly. And you just wonder,
Right.
why can't they figure this out? Well, today we're doing a deep dive into that very world, the world of data. We'll look at how we try to organize it, why it so often feels like a mess, and how modern systems can actually turn all those raw facts into really powerful business intelligence.
Right.
Our mission here is to unpack the core ideas behind databases and managing information using Laudon and Laudon's 17th edition of Management Information Systems as our guide. We want to give you a shortcut, really, to understanding why data is just as vital now as, say, money or people in a business, and why getting a handle on managing it is so key for your future, especially if you're heading into IT service management. If you find this valuable, by the way, please do like, subscribe, share it around, maybe leave a comment. It really helps us out.
And what's really interesting, I think, is that this isn't just technical stuff. We're talking about managing information systems, sure, but it connects directly to competitive advantage. It's about efficiency, making, genuinely smart decisions based on facts. For anyone starting an IT career or, frankly, anyone wanting to understand how organizations work with data today, these basics are absolutely essential. Foundational.
Okay, so let's start at the beginning then. Before we get into the solutions, the modern systems, we really need to grasp the problems, right? What was it like before data was managed properly? The Wild West of information, as you might say.
That's a good way to put it. In the past, companies often had these, well, we call them islands of information. Think separate systems for sales, another for marketing, maybe another for inventory. And this led to a whole bunch of headaches. The big ones were data redundancy and inconsistency.
Redundancy and inconsistency, like
Yeah.
getting 2 flyers from the same store.
Exactly like that.
Yeah.
Or maybe your bank sends a holiday card to your old address because you only updated it with one department, not the other. It sounds minor, but it's a real waste of resources. And honestly, it creates operational nightmares. Imagine trying to reconcile sales figures when customer names are spelled differently in 2 systems.
Yeah, I can see that. It's more than just annoying mail then. There must have been deeper sort of technical hurdles too.
Oh, absolutely. A huge one was program data dependence. This meant data was structured so specifically for one piece of software that using it with another program was almost impossible without basically starting over. Companies had to constantly reconstruct data. Think of the wasted time and money.
Wow, okay.
Then there was the lack of flexibility. Simple requests became huge challenges. If a sales manager needed data formatted differently than, say, the production team used it,
They were just stuck.
pretty much. Or they have to wait ages for IT to build something custom. Add to that generally poor security because the data was scattered, and a real lack of data sharing and availability between departments.
Yeah.
Well, you start to see why understanding how databases are properly built is so crucial for managers, for everyone, really.
It really paints a picture of, well, chaos, frankly. Constant inefficiency. So, if those traditional files were the problem, what was the big solution? What changed the game?
This is where it gets really interesting. The big leap forward was the database management system, or DBMS.
DBMS, okay.
The fundamental idea of a DBMS is to centralize an organization's data, put it all together into one system that serves everyone, effectively breaking down those islands of information we talked about. Think about it like organizing your desk. Instead of having paper in one drawer, pens in another, paper clips somewhere else,
Right.
you bring them all together when you need to work. A DBMS does something similar conceptually. It separates the physical view, like where the data actually sits on a hard drive or server,
Yeah.
from the logical view, which is how you, the user, see and interact with the data.
Ah, okay. So I don't need to know the technical storage details. I just need the information presented clearly, like the customer address on my report.
Exactly. It doesn't matter to the salesperson where the address byte is stored physically. They just need it to show up correctly and quickly. That desk drawer analogy really helps clarify it, I think.
It does. And having one central system just seems like such an obvious fix for all those problems. The redundancy, the inconsistency.
Precisely. A single, well-designed database drastically reduces those issues. It also separates the data from specific programs, making it much more independent and usable across different applications. And of course, it makes data far more available and generally more secure across the whole company. Which leads us to think about, well, what kind of database systems became the standard? What makes them tick?
Right. Let's dive into maybe the unsung hero here, the relational DBMS.
Relational databases, yes. They really became the foundation for decades, and for good reason. They organize data into tables. Think of them like spreadsheets, basically. Each table has columns, which we call fields or attributes, things like customer name or order date.
Okay, the columns are fields.
And each row is a record or tuple representing one complete entry, like all the information, for a single customer. Now, every record needs a unique identifier, a key field, like your student ID number, or maybe a unique order ID. That's crucial.
The unique identifier, right?
And here's the clever part. We use these keys to link tables together. A primary key in one table, like customer ID in the customer table, can appear as a foreign key in another table, like the orders table. That's how you know which customer placed which order. It creates the relation in relational.
Ah, okay. That makes sense. Primary key, foreign key links them. And I remember reading there's a sort of right way to design these tables, something about breaking down information, like not just having name, but first name, last name.
Exactly. You're talking about normalization. It's a process, a set of rules, really, for designing these tables efficiently. The main goals are to create the smallest possible useful fields for each piece of data. And critically, to minimize redundancy, avoid storing the same piece of information in multiple tables if you don't have to.
So normalization makes the data cleaner and more flexible.
Absolutely. It makes the whole database more adaptable, easier to update, less prone to errors when changes happen. Think about updating a customer's address with good normalization. You hopefully only have to change it in one place. Relational databases also give you powerful ways to work with the data. Key operations include select, which lets you pull out specific records that meet certain criteria.
Like all orders over $100.
Perfect example.
Mm-mm.
Then there's join, which is incredibly important. It lets you combine data from two or more related tables based on those key fields we talked about. So you could join the customer table and the order table to see customer names alongside their orders.
Yeah.
And finally, project, which lets you create a new, smaller table containing only specific columns from one or more existing tables. Very useful for creating specific reports or views.
It's really quite elegant when you break it down, but the power of a DBMS, it seems, goes beyond just storing and linking data efficiently.
Oh, much beyond. A good DBMS offers three really critical capabilities. First is data definition. This is basically defining the structure of the database and the characteristics of each data element. It ensures everyone in the organization is, sort of, speaking the same language. When marketing talks about customer address and logistics talks about shipping address, the system knows they might mean the same thing, defined in a standard way.
Consistency across the board.
Exactly. Second is the data dictionary. Think of this as the database's own documentation, or its instruction manual. It stores information about the data, what each field means, who owns it, how it's used, security rules, etc. This is vital for managing the database, for ensuring consistency, especially when people join or leave the team. It prevents a lot of guesswork and errors.
Like a central source of truth about the data itself.
Precisely. And third is the data manipulation language, or DML. The most famous one is SQL Structured Query Language. This provides users with tools to actually add, delete, modify, and retrieve data from the database. It lets people build queries, generate reports, and turn that raw data into useful information without needing to be, deep-level programmers.
Okay, so relational databases are clearly powerful workhorses, but the world's data isn't always neat and tidy rows and columns, is it? We're drowning in text messages, social media posts, videos, sensor readings. This sounds like big data.
That's the perfect term for it. Big data is often described by the 3 V's. Volume, just the sheer amount of data being generated, is staggering. Variety comes in all shapes and sizes, structured like traditional databases, but also unstructured text, images, sound, video. And velocity, the speed at which this data is generated and needs to be processed, often in real time.
So relational databases might struggle with that kind of scale and messiness.
They can, yeah, especially with the unstructured variety and the sheer volume. This is where non-relational databases, sometimes called NoSQL databases, really come into their own. They're designed to be more flexible, often handling huge data sets distributed across many machines. They're better suited for things like analyzing social media feeds or processing large streams of sensor data.
And speaking of distributing data, what about the cloud? That seems to have changed everything too.
Absolutely. Cloud databases are a huge deal. For smaller and medium-sized businesses especially, they remove the burden of buying and maintaining all the hardware and software infrastructure themselves.
Pay as you go, kind of?
Often, yes. Or subscription-based. It offers scalability and cost savings. Even large companies use cloud databases, maybe to handle peak loads or for specific projects alongside their own systems. It provides a lot of flexibility. And then there's a really interesting development, blockchain.
Ah, the technology behind cryptocurrencies.
That's where most people know it from, but its potential is much broader. Fundamentally, it's a distributed database technology. It creates a shared, immutable ledger of transactions. Each transaction is grouped into a block and added to a chain cryptographically. It's highly secure and transparent.
So useful beyond just finance.
Definitely.
Yeah.
Think supply chains tracking goods transparently, or verifying identities, managing digital rights. Anywhere you need trust and verifiable records across multiple parties without a central intermediary, blockchain has potential. It can reduce verification costs and risks significantly.
Okay, let's connect this back for, say, our graduate students or professionals listening. We have all these ways to store and manage data relational, NoSQL, cloud, blockchain. How do businesses actually use all this to get better, to improve performance?
That's the domain of business intelligence, or BI. BI is really an infrastructure, a set of tools and techniques for taking all that managed data and turning it into actionable knowledge. The goal is to help companies gather information, develop deep insights about customers, competitors, internal operations, and ultimately change how decisions are made to boost profitability or efficiency.
So BI is the bridge from raw data to smarter actions. What kind of tools are involved?
Key components include data warehouses. These are huge databases, often storing both current and historical data drawn from various operational systems across the company. The data is standardized and integrated.
A central repository for analysis.
Exactly. And sometimes, for specific departments or lines of business, companies create smaller, more focused versions called data marts, maybe a marketing data mart or a sales data mart. Using these allows managers to spot trends, maybe identify ways to cut costs, optimize inventory levels, understand customer behavior better, all sorts of things.
And for those really massive, often unstructured, big data sets we talked about, do data warehouses handle that?
Not always easily. That's where specialized tools come in. Technologies like Hadoop are designed for distributed storage and processing of huge data sets across clusters of computers.
Right, for the really big stuff.
Then you have things like in-memory computing, which speeds up analysis dramatically
Right.
by holding data in the computer's main memory, RAM, instead of on disk.
So much faster queries.
Orders of magnitude faster, often enabling real-time analytics. And you also have dedicated analytic platform, high-performance systems, specifically optimized for running complex queries on large data sets.
Okay, so you've gathered and stored the data, maybe in a warehouse or using Hadoop. How do you actually analyze it? What tools do you use to find the interesting patterns?
That's where analytical tools are crucial. One key technique is online analytical processing, or OLAP. OLAP supports multidimensional data analysis. Imagine your sales data has dimensions like product, region, time period, and customer type. OLAP lets you slice and dice that data, rotate it, drill down almost like twisting a Rubik's Cube to see different perspectives.
So you can easily compare sales of product A in the North region during Q3 versus product B in the South during Q4.
Precisely. It allows for very flexible, interactive exploration. Then there's data mining. This is more about discovering hidden patterns and predictive information in large databases. It uses statistical techniques and machine learning algorithms to find things you might not have thought to look for.
Like?
Well, common uses include finding associations, things frequently purchased together, like diapers and beer, the classic example, or finding sequences of events that often happen in order, like buying a house, then buying furniture. It's also used for classification, assigning customers to predefined groups, like likely to churn or high value. Clustering is similar, but finds natural groupings you didn't predefine. And forecasting, predicting future values based on past patterns.
So data mining can be incredibly powerful.
Immensely. Think about Chadwick's example in the text, tailoring sales offers based on analyzing past purchase histories. That's data mining in action.
But you mentioned a caution earlier about finding meaningless patterns,
Yeah.
like bottled water and white socks.
Right. That's a crucial point. Data mining can find correlations, but correlation doesn't equal causation. Just because two things happen together doesn't mean one causes the other, or that the relationship is even meaningful for business. You need business knowledge and common sense to interpret the results.
Good point. Now, a lot of valuable data isn't numbers, it's text, right? Emails, reports, social media comments. How do businesses analyze that?
That's where text mining comes in. It uses tools to analyze large collections of text documents, looking for patterns, key topics, or extracting specific pieces of information, analyzing call center transcripts for common complaints, for instance.
And what about analyzing website usage?
That falls under web mining. This looks at different aspects of the web. Web content mining analyzes the actual text and images on web pages. Web structure mining looks at how pages are linked together. And web usage mining analyzes user behavior, click patterns, navigation paths, how long they stay on pages. This is vital for optimizing websites and understanding user engagement.
And that can even tell you how people feel.
To some extent, yes. Sentiment analysis, often using text and web mining techniques, tries to determine the attitude or emotion expressed in text, like whether customer comments on social media are positive, negative, or neutral about a product. It's really valuable for reputation management.
Fascinating. And finally, tying this all together, the web itself plays a huge role in making databases accessible, doesn't it?
Absolutely. It's become the universal front end in many ways. Using a standard web browser to access internal company databases is often much easier and cheaper than developing custom client software.
Less training needed, too, presumably.
Exactly. Everyone knows how to use a browser. It also allows companies to provide access to data from older, maybe less flexible legacy systems without having to completely replace them immediately. You can build web interfaces that pull data from multiple back-end systems, giving employees a single integrated view of information right in their browser. It really enhances accessibility and usability.
Okay, all this technology, DBMS, data warehouses, mining tools, it's incredible. But it hinges on one thing, right? The data itself has to be good, accurate, reliable.
You've hit on arguably the most critical point. All the sophisticated analysis in the world is useless or even dangerous if it's based on bad data. This brings us to data governance.
Governance, that sounds important. What does it involve?
It's essentially about establishing the overall strategy and processes for managing corporate data. It specifies the policies, the rules, the standards, the accountabilities. The goal is to ensure data is available, usable, has integrity, meaning it's accurate, consistent, complete, and is secure. It also includes complying with regulations like Sarbanes-Oxley in the U.S., which has strict rules about financial data accuracy and security.
So it's the high-level framework for managing data as a valuable asset.
Precisely. And working hand in hand with governance is data quality assurance. This is more about the operational activities to ensure the data meets those standards. Think about your own college records, as mentioned in the text. What if your grade was entered incorrectly, or your address was wrong? Bad data can have real, tangible consequences: losing financial aid, missing important communications, frustrating customers, making poor business decisions.
Right. So how do companies actively check for these problems?
They use data quality audits. This can involve surveying data files, analyzing samples of data for errors, or even surveying end users to gauge their perception of data quality. Are they constantly finding errors? Do they trust the data? The goal of these audits is to identify problems, which then leads to data cleansing or data scrubbing.
Cleaning the data.
Exactly. Identifying and correcting incorrect data. Incomplete data, improperly formatted data, redundant data. It's an ongoing process because data is constantly changing, but it's absolutely vital. The cost of not addressing bad data in terms of wasted resources, poor decisions, lost customers, even regulatory fines is almost always far higher than the cost of ensuring data quality.
It really underlines that data isn't just a technical issue, it's a core business function. So what does all this mean for someone maybe starting their career or studying information systems right now?
It means understanding these concepts is fundamental.
We've really covered a lot of ground today. We started with those frustrating islands of information in the old traditional file system.
Yeah, the Wild West.
And journeyed all the way to the really sophisticated intelligence systems, relational databases, data warehouses, big data tools, BI, that power modern businesses. Grasping these foundations, from how relational tables link together to why normalization matters, to the challenges of big data, and especially the critical importance of data governance and quality. It's not just academic. This is the bedrock knowledge you need to actually create value in an organization using information technology.
Absolutely. The skills we've touched on: understanding database design, knowing how to query data with SQL, appreciating the goals of BI, recognizing the need for data quality. These are precisely what employers are looking for. Whether you're aiming to be a data analyst, a database administrator, an IT manager, or involved in any aspect of IT service management, you'll be working with these systems. You'll be part of transforming raw data into a genuine competitive advantage for your organization. It's exciting stuff.
It really is. And as data just keeps growing faster, bigger, more varied, and we see technologies like AI and machine learning getting woven more tightly into these data systems, it makes you wonder, what new challenges or maybe ethical questions do you think we'll face in how we manage and use all this information in the coming years? What opportunities for innovation might emerge? Something to think about.
It is a great question to ponder. The landscape is constantly evolving.
Definitely something for our listeners to consider. Well, that brings us to the end of this deep dive. Thank you so much for tuning in. And again, if you found this discussion helpful, please like, subscribe, share, and we'd love to hear your thoughts in the comments, especially on that final question about the future of data management.